I'll talk about harmonic motion, which is very important in the study of vibrations. As we know, the vibrations depend on the oscillatory motion. And the oscillatory motion may either repeat itself regularly, like in the case of periodic motion, like here, the motion repeats itself over a period, or it might be irregular, like in the case of an earthquake, for example. Now, the periodic motion is very important for us. The motion that repeats itself after equal intervals of time, like these intervals of time, is called periodic motion. So the one at the top is a periodic motion. Now, there is a special kind of periodic motion which we say is very important for us, and it is the simplest kind of periodic motion, and we call that the harmonic motion. Harmonic basically means that it is made up of either of sine or cosine functions, and it is of single frequency. It contains a single frequency, which is this omega inside in this motion. Okay. So it is described by a sine function, and what we call a harmonic motion is the motion that is described by sine or cosine functions. As a physical example, I'll give you the Scotch yoke mechanism. In this mechanism, we have a crank, OA, that drives a vertical rod that has a horizontal slot. It has a vertical guide R. So as this thing, as this crank rotates, it makes the slotted rod go up and down. Okay, and this crank rotates with a constant angular velocity omega. Therefore, the displacement angle theta is equal to omega t, and the vertical displacement you see here in the rod, slotted rod, is a sine omega t. So the vertical displacement, which we call x, is a sine omega t. This is directly transferred to this mass that is over here. So the displacement of this mass is also a sine omega t. So it is the mass m experiences a harmonic motion, which has a single frequency of omega. The displacement of the mass about its middle position, which is this position, is a sine omega t. A being the amplitude, omega being the frequency. We'll come to that. Now, if you take the derivatives of these, you find the velocity and the acceleration of the mass. Velocity is derivative of a sine omega t, which is omega a cosine omega t, and acceleration is the derivative velocity, which is minus omega squared a sine omega t. So we find out that the acceleration here is proportional to the displacement. And this kind of motion, we exactly call this kind of motion as the simple harmonic motion. Simple harmonic motion is the name we give to this kind of motion. So this is the physical example. The harmonic motion can be generated by a rotating vector, just as in the case of the crank, which rotates about a circle, let's say a vector that rotates about a circle, at a constant angular velocity omega, so that this again is omega t. And as you see, the horizontal component is, the vertical component is a sine omega t, and the horizontal component of displacement is x is equal to a cosine omega t. And we call the functions sine omega t and cosine omega t as harmonic functions, as we have said. Now, here we have plotted the sine function and the cosine function horizontally and vertically. Both are harmonic functions. which are very important in vibrations. By the way, sine and cosine functions, for our purposes, are more or less the same function. The only difference is the phase difference between them. We will come to that. So the harmonic motion is, as we have said, is described by a sine or a cosine function, a cosine omega t, a sine omega t. AB is the amplitude of the motion. For example, how much peak it makes is the amplitude. Okay, from 0 to its peak is the amplitude. Period is the time taken from one position to the exact same position, like this one. Okay, the period is capital T is given by 2 pi over omega, and omega is the frequency, but it is the circular frequency that is measured in radians per second. So if you remember the rotating vector makes 2 pi radians in one rotation. So the period is 2 pi over omega. The derivatives, as I have said, of the sine omega t is again omega a cosine omega t, and omega minus omega squared a sine omega t, which is equal to minus omega squared x. So the acceleration is proportional to the, as we see, the displacement. Okay, there is the difference of the phase between two harmonic motions. Let's say that you have two functions which are harmonic and they are of the same frequency, let's say. For example, this one is 2 pi t, so its frequency is 2 pi, and this one is 2 pi t plus pi over 2. The blue one is 2 pi t over plus pi over 2. The only difference between them is the phase difference. And as you see, there is a phase difference of pi over 2 or 90 degrees between them. So the red one is a sine function. The blue one is a cosine function, actually. So the phase difference makes a shift of the function in one direction, in the negative direction, actually. For example, if you have two functions which have different amplitude but of the same frequency, they might also have a phase shift. This phi is the phase shift. In this case, two vectors are rotating with the same speed, but there is a phase angle difference between them. This P1 and P2 angle between P1 and P2 is phi. And if you plot the horizontal components, we get such a picture, as you see. X1 is the solid line, and X2 is the broken line. As you see, amplitudes are different in this case, but also the phases. There is this much of phase difference between them. It might be a little complicated in the beginning. But if you shift A2 an amount of this much, that is a time amount of phase, in that case, they will be exactly collinear, although the amplitudes would be different. Okay. Now, another thing is the harmonic motion can be expressed either by a, as I have said, amplitude and its phase, two parameters, and its frequency, of course, or you can express it as a combination of a cosine and a sine function. Okay, this is also possible. You, instead of expressing it in terms of the amplitude and phase, A and B are the amplitude of the cosine and amplitude of the sine. How do we find A and B? Let's try to find them. We can open up x sine omega t plus phi in terms of its trigonometric expansion. And as we see here, the coefficient of cosine omega t, which is A, is equal to x sine phi here, x sine phi. And the coefficient of sine omega t will be x cosine phi. Now, if we square these if we square a and if we square b, a square plus b square will be x square times sine square phi plus cosine square phi. Sine square phi plus cosine square phi will be 1. So x will be simply, the amplitude will be a squared plus b squared. On the other hand, the phase angle phi would be, if you divide the expression of a to b, you will get tangent phi. So phi would be tangent inverse of a over b. So these two forms of harmonic motion are interchangeable and they can be used in place of one another. You can either use this one or that one. All these, both forms are acceptable. Probably this is a cleaner expression, the first one, and it is used more commonly.